So you want to solve Laplace's equation in this more complicated region. We've got a disk, or in 3 dimensions a cylinder, which is above the plane, and if we imagine this extended into 3 dimensions, so we can think of it as disk, or in 2 dimensions, or as a cylinder coming out of the board above an infinite plane. We want to find Laplace's equation in this region. So to do this, we can we use a conformal mapping to transform this z-plane into an annular region. So we've done this before. So an annular region where the outer radius is 1 and the inner radius is a constant I'm going to call c. And so this is now the w plane. So this side here of the cylinder gets transformed to this bit here. So this is going to be v naught. Let's call this v tilde equals v naught, and this bit, this region here will get transformed to the unit circle. So this is v tilde equals 0 out here, and again inside here we've got del squared v tilde is 0. V tilde is a function of u and v. So the transformation w equals f of z we used was somewhat complicated. It was w equals z minus I e squared minus a squared over, it's actually just a bilinear transformation. Not all that complicated. And the value of c in terms of a and b we worked out before was this expression, which I'll just write down, and then I'll call it c from now on to save lots of writing. So we know that since this is a constant potential here and a constant potential here, we can write the solution as some constant a times log of mod of w plus some other constant b. Now, we can immediately simplify things because we know that when mod w is 1, we know we want the potential to be 0. So that means that b has to be 0. So we can cross off this, and we've just got v tilde, which is a function of u and v, is some constant a times log w. Now, to find out what a is, we know that when log w is c, we need to have v tilde equals v0, so we're using that. So v0 equals a times log and mod w, so w has to be c. So that means a is v naught over log c, and we've got this is v naught over log c times log w. And then I'm ready now to just use this expression here. So now I'm going to rewrite things in terms of z. So I now, instead of using tilde, I can actually just write v of x and y is equal to v naught over log c times log of this, log of mod of this. So it's the modulus of this Now, the modulus of w is the square root of this times its complex conjugate. So what I can do to simplify things is write the square root of taking the square root with a log sign, all I do is have a factor of 2 here. So then it's going to be w times w star. So I don't need the mod sign anymore. So w times w star gives me, when I do the w times the w star on the bottom, I get something real on the bottom. So I actually only need to, okay, I'll do this thing a bit more slowly. So let's think. No, so I was thinking of arguments. Right, so no, I need both of these. So when I take times the complex conjugate, if I can do it, I'm going to have x. This should be straightforward. Yeah, I just need the magnitude of this. So if I multiply by the complex conjugate, so the magnitude of this squared is going to be x squared, real part, and the imaginary part is y plus the square root bit. So that's all squared. It's y plus the square root bit, all squared. And then the top bit, when I multiply that by the complex conjugate, I've got the real bit is still x, so that's the real bit squared, and the imaginary bit is now y minus the square root, so I've got that thing squared. And that is the final answer.